Alright everybody, welcome back. This is our third video in the Chapter 21 series, so I am going to pick up where I left off. Last time we talked about addition of primary amines to aldehydes and ketones, and as we saw, that made something called imines, right? Carbon-nitrogen double bond. We're going to try something a little bit different now. We're going to do addition of secondary amines. And again, this is going to be with aldehydes and ketones. Can't spell. Good enough. Alright. So, just like with last time, what we need is an aldehyde or ketone. So, simply speaking, just in rough form, if we take an aldehyde or ketone, and we add a secondary amine. Remember, a secondary amine is going to have two R groups on it. And again, just like last time, we're going to be using mild acid. Okay? This time, we're going to get something called an enamine. And I'll show you the structure of that in just a second. But you can probably tell from the name, enamine, there's a couple of distinct portions. You have an amine portion, a distinctly nitrogen-containing group, and you also have the ene. And what do you think of when you hear ene? You think of alkenes. So there's going to be a carbon-carbon double-bonded section in here too. All right. Let me show you, an example of this. So, for example, if you took something like acetone, right? And I really should have put equilibrium arrows on the above reaction. This is another reaction that goes at equilibrium. All right, let's say we had just a basic secondary amine, a couple of CH3 groups attached. Here's what our product would look like. Okay, and so you can see where we get the term enamine from. Here's the ene portion right over here, carbon-carbon double bond, and here is the amine portion. You have a carbon-nitrogen single bond, which is traditionally recognized as an amine. All right, so let's see how we can actually get to this. We're going to go over the mechanism, and you're going to see it's going to be pretty similar to what we did with the primary means, the imine formation, but with a key difference. All right, so let's see. We'll just use this. We'll take an aldehyde. If you hear any noises in the background, that's just my daughter being annoying.
Hey!
Hee hee. All right.
I'm not trying to be.
Shh. Okay, so there's an aldehyde. And let's see, we're going to use this secondary amine. And with H3O+. Okay? So the mechanism, like I said, in large part is going to be very, very similar to what you saw with reaction with primary amines, right? You're going to have an initial attack, nucleophilic attack of the nitrogen on your oxygen, your carbonyl oxygen, and that'll promote a pair of electrons. Okay? So you're going to get this. And we can solve this very easily by having a proton transfer, right? That oxygen will grab, that proton. And that'll satisfy both charges. And this should look familiar. This is a carbanolamine, just like the intermediate was in the previous reaction, right? Alright, so, just like in the last reaction, once you get to this point, that oxygen's going to grab a proton from H3O plus to form water. We're seriously running out of room here. Alright, that water's going to leave, and at the same time, a pair of electrons from the nitrogen is going to swoop down to make a double bond. Just like that. Okay? All right. Now, once we get to this point, though, what is actually going to happen here is that, one second. Oh, yeah, forgot a positive charge. I knew I was missing something. And nitrogen has a positive charge. All right, so once you get to this point, this is going to be the part that's going to be a little bit different. All right? What's going to happen next is that on this carbon, right, the one that's directly adjacent to the carbon-nitrogen double bond, you're going to have a hydrogen, and that's going to be plucked off by a leftover water. These electrons will form a double bond here, and that'll force this pair of pi electrons back up to nitrogen. And Viola, that creates the nitrogen-carbon single bond. And now you have a double bond directly adjacent to that. And that is the formation of your enamine. All right? So this mechanism goes exactly the same as the imine mechanism does up until this point right over here. Okay? The reason being is because, to satisfy that positive charge on nitrogen, when you formed imines, the nitrogen has an H you could just take away and directly make it neutral. Here, the nitrogen does not have an H that you can take away, so it has to find one somewhere else. Okay? So that's why you get the carbon-carbon double bond and not a carbon-nitrogen double bond. All right, let me show you another one. Hopefully I'll be able to manage the screen a little bit better on this one. Almost ran out of room that time. All right. Let's do this with acetone. All right, and just to make this interesting, we can even use something kind of exotic looking. We can use a cyclic amine. You can see it's still secondary, so it still qualifies. Now the mechanism is going to work exactly the same here. So this is a bit of review, right? But I just want to make sure that you guys got it. So you're going to have a nucleophilic attack on the nitrogen, on the carbonyl carbon. You're going to move a pair of electrons up. Get your negative oxygen. Your positive nitrogen. Proton transfer. A little stray mark there, getting rid of it. So that gives you your neutral OH. And your neutral nitrogen gives you to your carbanolamine, right? Then guess what? We got that H3O plus. That H3O plus is going to protonate your oxygen. Creates water. Water's a good leaving group, so guess what? It leaves. Electrons on nitrogen swoop down to make a double bond. Now nitrogen has a positive charge. Everything up to this point has been exactly the same as the imine reaction. Now, of course, remember, H2O is going to try to satisfy that positive charge, so it takes off an H from an adjacent carbon. These two carbons both have H's, right? They're exactly the same as symmetrical, so it doesn't matter which one we take. I'll just grab this one. These electrons move back into a double bond. These electrons move back to nitrogen. And voila, we've got our enamine. Okay. All right. So you see, the mechanism's a bit involved, but like I said, if you know the imine mechanism, and you can remember that one additional change at the end, then you should be good. All right. Now, even aside from the mechanism, it's pretty easy to just simply predict the products from these. All right. You just have to remember some patterns. All right. And you can even do this in more complex situations. Let me take one like this. Come on. There we go. Let's see, and we'll make diisopropylamine this time. Okay, so I'm not going to go through the mechanism of this one, right? But you'll recognize from past examples that basically what we do here when we get to the product, when we get to the enamine, is that carbonyl group, that C double bond O, always changes to a C single bond N. All right, so if we're thinking about products here, I'm just going to draw the products down below. You know whatever product we get is going to have a carbon-nitrogen double bond. And then you just write in the R groups that are attached to that nitrogen. Right? So that's your amine linkage. Now you have to find your ene linkage, your alkene linkage. Remember, the alkene group is always going to be a carbon from your carbonyl carbon double bonded to an adjacent carbon. Right? And that adjacent carbon, somewhere in the mechanism, at the end of the mechanism, has to have lost an H. All right? This is an interesting example because, you see, right here and right here, we have two adjacent carbons. They each have H's, but they are different from each other. So this is going to be a case where we do get a mixture of products. You could form the double bond right there, or you could form it at the other carbon right here. So these would both be legitimate products, legitimate enamine products of this reaction. Right? So just be sure to watch out for that whenever you're doing your problems. Okay? All right. Erase, erase, erase. What about tertiary amines? We haven't done those yet. What if we had something like this? Whoops, stray mark. All right, tertiary amine is going to have 3 R groups on it. Let's just say I put 3 methyl groups on it, right there. All right, and we did this again in mild acid. Any ideas what you would get there? If you think about it, actually what's going to happen here is you're going to get a no reaction. Any ideas why you're not going to get a reaction here? Think about it for a second. Whenever there's a no reaction, there's always going to be a flaw in the mechanism somewhere, right? And that's exactly what we can see here. If you want to try to go through the mechanism, it starts off the same way as usual, right? You could do that. Have nucleophilic attack at your carbonyl carbon. You create O minus, and you create a positive nitrogen. Now, how do you satisfy those charges? Well, what did we do the last couple of examples? Excuse me. We had a proton transfer from nitrogen to oxygen, right? But we can't do that this time. We don't have any H's available on the nitrogen, so we can't have a proton transfer. Sorry, I just dropped my stylus, so I've got to find it on the floor now. Give me a moment. I could either start the video over and have it nice and smooth, or I could have this in here, so I'm just going to have this in here. Robin, do you see my stylus anywhere?
Which one?
The little one?
Nope. I just saw it with you whenever you were using it.
Well, crap. Okay.
Here's the big one.
Technical difficulties here. Have to use my big stylus, sorry about that. But anyway, we have no reaction because the mechanism basically gets interrupted at this point. Alright. Just to let you know when I'm talking about big stylus, little stylus, I have a smaller stylus that I use for the writing and a bigger stylus I use for erasing because the fat stylus makes it too big for the screen a lot of times. So I'm going to be writing the rest of my notes in this video with the fat stylus, so we'll see how that goes. Alright. Okay, one other interesting thing that we can see is we can take imines and we can take enamines and we can hydrolyze them. They can undergo hydrolysis. So, if you remember, we previously talked about hydrolysis in another chapter. We said that hydrolysis is basically a general term that means that you're using water in some way to break down a larger molecule into smaller pieces. All right? And that's exactly what we're doing here. Basically what you can do is you can take an imine or you can take an enamine and you can hydrolyze them to form their original parts. You can form the original aldehyde or ketone and the original amine that was used to make them. All right, and it's pretty simple. I'm not going to go through the mechanisms, but I'm going to show you how to predict the hydrolysis products. All right, if you take something like this, right? This is an imine. We have a carbon-nitrogen double bond. All right, what you do to hydrolyze an amine is you simply use acid. And we used acid before, but in this case, we make a strongly acidic solution. Not strang, I misspelled it. Strong. All right, so this will be like pH 1 or so. All right, and basically what this will do, this will sort of cleave your imine at that carbon-nitrogen double bond. So all you have to do is remember to cleave it here. You replace the nitrogen with an O, and there you have your original ketone. And then you have this nitrogen fragment, all right? Just add H's to fill out its valency, and then boom, you've got your answer, right? Very, very simple to predict the hydrolysis products of an imine. All right, you can do the same thing with enamines. Can be a little bit trickier, but honestly, it's pretty simple. All right, so let's say we had this guy. All right, there's an enamine, and again, we're going to add H3O, strong H3O. All right. Well, again, you can look here. There's a basic bond that we're going to have to cleave. We're always going to be cleaving that carbon-nitrogen connection. In this case, it's a single bond. All right, so that's going to create your fragments. All right, so when you do this, you get, first of all, the amine. Right, you know it's going to have a nitrogen with the methyl and a propyl. That means you just simply have to add an H to it, right? So that's easy. That gives you the amine product. All right, and then you have the cyclohexane component, right? What you do is you remove the double bonded carbon, you remove the carbon-carbon double bond, excuse me, and you replace it with a carbon-oxygen. double bond. And boom, there you go. Okay? So cleave it here between carbon and nitrogen. Add an H to the nitrogen to get the amine. Replace the alkene group with a carbonyl group to get your aldehyde or ketone. All right. You know, usually when I erase stuff on the board, I like to ask for questions. I guess I can't really do that here. But you can be thinking of them, and you can definitely send them to me anytime you would like. All right. There's going to be one other reaction I want to cover here in this video, and that is something called hydration. And just as you can probably tell from the name, hydration, you're going to be basically adding water to something. And again, this is all with aldehydes and ketones. So basically what you do is you take an aldehyde or ketone. These, again, are equilibrium, reversible reactions. You add water, either in the presence of acidic media or basic media. Works the same either way, just goes by different mechanisms. All right? Either way, you get something called a gem diol. All right? We've run into the phrase gem before. Gem is short for geminal, and that means on the same carbon. So if you have a gem diol, that means that, you know, here's an example of a gem diol. It just simply means that you have two OHs that are on the same carbon. Okay? And the mechanisms are pretty simple for this, especially the first one. So, basic media is going to be the one I'm going to show you first. All right, so let's say we have an aldehyde. Let's just say we have this guy right over here. All right, and we add water in the presence of OH minus. Okay? So, if you're looking at this, obviously OH minus, you know, is a strong nucleophile, right? So, you're going to have a nucleophilic attack on that carbonyl carbon. These electrons are going to move up to the oxygen. Give you that. And then the water acts as a proton source for that negative H, and boom, there's your product. There's your gem diol. Very, very simple process. Yeah. Now the acidic process is a little bit more involved, but not much. It's still pretty simple. All right, let me show you how that one works. I want to work with the same aldehyde here. Come on. My fat stylus isn't working very well. So we're going to do this in acidic media. So water in acidic media forms H3O+. So we'll start there. Okay, now this one's going to be a little bit different because now we don't have a good nucleophile sitting there right off the top of that. We have an acid. So an acid's going to want to give off an H, and what's going to accept that H? Well, it's going to be your carbonyl. Okay, so that creates a positive oxygen. Now, oxygen hates being positive, right? So it's going to pull on those electrons in the double bond even more strongly now, and that's going to create an especially strong partial positive on that carbonyl carbon. So at that point, the water that's left over can nucleophilically attack, drive electrons back up to oxygen. Okay, and the last thing is you got to get rid of an H on that water. So another water molecule that's in the system can come by, grab one of these H's, and that creates your gem diol. A little bit more involved than the basic situation, but not too bad. All right. One last thing is I just want to show you is kind of an interesting, just sort of an interesting situation in which these guys can be found. This reaction can be found. There is a molecule called chloral hydrate. All right, and chloral hydrate is commonly used as a sedative for various types of things. It can be used as a sedative in sort of a hospital situation. Also, if you've ever seen old movies, you see this in old gangster movies a lot too. You'll see somebody slip like something in somebody's drink, and they'll say they slipped them a Mickey. You guys may be too young to really know what I'm talking about here. I guess in a way it's similar to roofies, except it's an entirely different molecule. But yeah, in old gangster movies they would call it slipping a Mickey. Chloral hydrate is actually made via this process. So this is what chloral hydrate looks like. Or excuse me, this is the precursor to chloral hydrate. You see, basically, it's just a simple aldehyde, except one of your carbons has 3 chlorines in place of the H's. But yeah, this can be made, this particular molecule can be converted into the hydrate form very easily using the same type of techniques that we just talked about. So, if you ever see the old gangster movie and you hear about somebody slipping somebody a Mickey, know that that Mickey was probably made via this process. Alright guys, that's all I have for today. Read up on this one, the material here, watch the video, make your notes. Be sure to get me any questions you have. Alright, until next time, I will talk to you later.